This is a production of Cornell University.
All right. So if it's about oxygen, what are we talking about? We're talking about respiration. Okay? So when we talk about redox and respiration, we're really talking about basically a biologically mediated reaction. And that's respiration. It's basically how we get ATP. I mean, we're taking oxygen, we're eating food, some sort of organic material with oxygen. We transfer the electron to make CO2 and water, and as a byproduct, or I should say these are the byproducts, and the product for us is making ATP for biological activity. Okay? It's all about getting energy. And so if we're going to start talking about getting energy, we're going to have to talk about the electron tower. We're going to have to talk about where that energy comes from. And I don't know if you guys remember this. This is, let's skip over this one. Have you guys seen something like this lately? You probably all have seen something like that. We're going to talk about that in a moment. But this is basically the electron fall, the electron tower. Okay? When we talk about redox, reduction, oxidation potential, we're really talking about the potential of one substance to accept or donate an electron. And in that acceptance or donation, there is an energy exchange. There is a certain amount of energy that's released that can be captured. Okay? A couple of examples here. This is iron, +2 form, plus water, moving to +3 form, plus proton, and those 2 electrons. Pair that reaction with oxygen and hydrogen, that electron, 2 electrons. This is the complete reaction. I do not expect you guys to memorize this, but what's important is to understand that these are paired reactions. For a substance to donate an electron, it actually has to have something that's going to accept that electron. Okay? They happen at the same time. They're simultaneous. The electron does not exist freely. Okay? We sort of draw it like it's free, floating around, but the reality is that this is come from that, and this is going into that. Okay? These reactions occur simultaneously. That's the first thing that we need to remember. The second thing is that this reaction produces electricity, volts. Okay? It's a potential. Okay? It's basic, and when we look at this, we're basically looking at we're measuring this voltage is a measure of that tendency to the tendency of these substances to accept and donate these electrons. Now, the charge numbers that we use is based on a reference state. It's sort of the half reaction. That reference state is the amount of electron energy that you convert from taking basically a H2 and converting it into H. Okay? We arbitrarily set that at 0, but that's the default. I mean, don't worry about that. But what is important is more positive the energy, that's the energy, the measure of the redox, EH, the easier it is for that substance to be used as a terminal electron acceptor, i.e., it's going to accept that electron. Okay. Let's take a look at the tower, and hopefully some of this will become a little bit more apparent. Remember, this is a paired reaction, so you're looking at the pairs. Okay, so it doesn't matter which one of these pairs you look at. Let's look at this one, the nitrate-nitrite one. The first in this pair is the oxidizer, this one right here. It is going to be the one that accepts the electron. The second in the pair is going to be the one that donates the electron. Okay, second in the pair is reducer, it donates the electron. Now, these guys are not doing it to each other. They're basically doing it to other substances. Okay, so the classic one that we look at is this, because this is what we do. CH2O, some sort of organic molecule, food, plus oxygen. This will go to H2O plus CO2. Right? Actually, I should do that the other way. But this exchange is going to produce a certain amount of energy. Okay. Let's look at that one in particular. CO2 is the acceptor or the donor. We're looking at CO2 up here. Oop, did I skip the right one? Yeah, okay. Oh, the hours are wrong. This red arrow is supposed to go to the food molecule on the top. Sorry. Okay? So if we take CO2, the pair CO2 and CH2O, CH2O is the food that we're eating, okay, and we respire with oxygen, okay, so the first one is the oxidizer, it accepts the electron. The second one is the reducer, it donates it. So the second one is the food, okay, the CH2O, that is going to donate an electron to the acceptor, the oxygen, O2, right? Okay, so here's my electron. It's going to be transferred to this guy, right? My electron's going to jump. Make sense? In the process, the CH2O is going to be reduced to CO2. The first in the pair is the oxidizer. It's accepting it. Okay, so it's going to be reduced to CO2. So this guy is going to become that. Right? This guy right here, the guy who accepted it, is going to become the water. This is going to become that. And in the process, the amount of energy that was released basically is 0.5 down to 0.82. Or I should say negative, let me say this differently, negative 0.43 to positive 0.82. You add those two up, and you basically get, I actually made it, some rounding error is there, but basically you're going to get 1.2 volts of energy. That energy is then applied to making the ATP. Does that make sense? The larger the fall, the more energy you're going to get. So if I started here and I ended here, the delta between them, 40 to 20, is I'm only going to get 0.6. Does that make sense? All right. Here's another reaction using food, but rather than using oxygen as an electron acceptor, system goes anaerobic. We start using iron, right? We talked about this. Use iron, I get less energy per value. Oxygen, I get 1.229. Iron, I get 1.19. Makes sort of sense? Questions? All right. Take a deep breath. We're past the electron tower. Okay? And what I want you guys to look at now is a series of rather important reactions. Now, when you look at something like this, you often think, well, that's the only reaction that's going on. But the reality is there are a lot of reactions going on at the same time in these systems. There's a lot of elements out there. There's a lot of molecules out there that can be used as food. And there's a lot of different elements that can be, or molecules that can be used as electron acceptors. So when I say, you know, we're getting a really good bang for our buck because this is oxygen and food that we're using, okay, it's not to say that the other organisms out there that are not using oxygen aren't getting energy as well. They're happening at the same time. It's just that in the presence of oxygen, you get the largest amount of energy. That's why the oxygen breathers are so successful. We can get more energy for the amount of food that we eat. Okay, so here are some of these elements: carbon, nitrogen, sulfur, iron, magnesium, or manganese. Okay, here's some of the well-known oxidized form. This is basically CH2O. This is basically food. Okay? These are the reduced forms. Okay? Methane, so on. Nitrate versus ammonium or nitrogen gas. Sulfate versus sulfides. Okay, that's just, there's a lot of them. You don't have to memorize them, but I want you to picture in your mind that there's a lot of these reactions going on at the same time. Okay, here are the half reactions. This is basically these reactions lined up next to each other. I highlighted some of the ones that we see a lot of, but basically here's the amount of energy that you'll get from that paired reaction. Now I want you to see something here. You'll notice that as you go up, you're seeing more and more and more energy released, but you'll note that oxygen's here. So that oxygen reaction with food doesn't actually mean it's the biggest amount of energy that you can get out of it. Okay? There are, in fact, other elements or substances that can accept electrons and donate them that you can get more energy from them. So I'm posed the question then, why is oxygen so important? The answer is way back here. It has to do with abundance. There's a lot of oxygen out there compared to these other elements that can be acceptors or donators. There's a lot more oxygen out there than there is manganese oxide or manganese by itself. Does that make sense? Okay. Now, a couple more slides. What's going on in this slide? Okay, we're looking at oxygen in the soil. Okay, this is basically a percent, so 2 to 18, and we're looking at days that we let that soil dry. We basically take that soil out and we put it on the surface and let it drain out. Okay, now this redox potential basically represents the move of this electron tower from this zone where it's wetter to that zone where it's drier. Okay, so the amount of electron fall is going to increase as the system gets drier. So as the O2 content increases, we have more oxygen to be used as an electron acceptor. And so as a result, the redox, the total redox potential of that soil increases. Now, remember, we've got lots of redox reactions happening. Oxygen is not the only one that is increasing as the system gets drier. What happens to reduced iron when the system goes drier? It goes from Fe plus 2 to what? Fe plus 3. We're basically shifting it from here to here, which moves this reaction, let's go this one, basically from here to here. Does that make sense? So here, how much energy am I getting out of it? But if I start moving it up, I'm getting more energy.
Sorry, what
So if I move from the Fe plus 2 form to an Fe plus 3 form, okay, I'm now making the soil volume have more things that it can accept electrons. And that energy boost is up to here.
But what causes the change?
The cause of the change is the amount of energy that I'm potentially getting out of this system. Because if I have a lot of Fe plus 2s, it's not going to accept any more electrons, right? But if I have Fe plus 3s, I can add electrons to that, and I now have that as an energy source, which in a reduced system I don't have. All right.
So I guess what I'm asking is, what are the conditions that would, in the soil, that would make it move from Fe plus 2 to Fe plus 3?
Okay, so the question is, what are the conditions in soil that would make Fe plus 2 move to Fe plus 3? And we can sort of go back to our story about modeling for that one. What happens when the presence of oxygen with Fe plus 2? Go straight to Fe plus 3. Right? So as my system gets drier, yeah, I'm moving more oxygen, so I'm using that as an electron acceptor, but I'm also increasing the amount of Fe plus 3. So if I have an Fe plus 3, this can accept an electron. So I now have more potential than if I had an Fe plus 2. For this to accept an electron, it actually has to go to Fe plus 1. And I don't think that actually exists.
So basically, as the system dries, your Fe plus 2 starts turning into Fe plus 3, which can accept more electrons
Right.
than the Fe plus 2 can.
Right. As your system goes dry, your electron tower moves more negative, goes up, right? Which means the separation between using food as the electron donor and finding some sort of electron acceptor, that drop gets bigger, which means I get more energy out of it. So my EH, my potential, is going to increase as the system dries. It's not just about oxygen, it's about all these other things that are changing as well. Go.
Is food always an electron donor?
In some systems, so the question was, is food always an electron donor? And generally it is, but I think there are a couple of scenarios, and don't quote me on this one, but I think there are actually a couple of scenarios in anaerobic systems where food is actually not necessarily used as, it can in fact not be an electron donor. Because when we think of food as both energy and nutrients, but often food can be, we're just using, for us it's mandatory, but there's a lot of different organisms out there that will use one substance for energy and another substance for nutrients. And I think if you get to a system where the organism is dying and it needs to have food versus something else, it will use energy to get nutrients, or it will use nutrients to get energy. And so they'll play a game between the substances that they're respiring or consuming. But I don't know the anaerobic systems all that well. Okay, we're good with this? Does this make sense? Questions so far? Okay. This is a scenario we're basically looking at a temporal change, a change in time. But we also can look at a change in space. Okay, same time. Basically what you're looking at is a core. This is the aggregate, okay, a large aggregate. Basically this is the center of the aggregate and distance from the aggregate. So here's 0, here's 3, here's 3. We're going towards the edges, okay? And here's distances again. And basically what you're looking at here is the oxygen content. Each one of these isopleth lines is an oxygen content line, okay? So this core in the center right here is 0% oxygen. And as I get closer to the edge or farther out from the core, I get more and more oxygen. Okay, so what is that going to tell me if I look at this as a graph like this? Where is more of my redox potential? On the edges. Okay, there's more oxygen out here, right? And this is a great example of if this system starts drying on the edges, the water that's in here through capillary action, what's going to happen? It's going to start migrating out to the edges. And if I have a reduced system in here, there's no oxygen in here, okay? Which means all the material that's moving out to the edges is reduced material, right? And if it happens to be iron, moves to the edges, what's going to happen to it? It's going to oxidize and turn red. So I can not only use those patterns of color to give me an idea about redox potential, but it also can tell me a good idea about oxygen content. Where are the organisms that are going to be anaerobic respirers versus aerobic respirers going to be? So right there, I can take a look and I can say, this is the distribution of my population. Now, granted, this is a temporal thing. You give this enough time, and the oxygen content is going to increase in there, but you can certainly see the behavior of different organisms change as that oxygen content changes. Cool? And it all goes back to this tower. It all goes back to this because they're trying to respire. They're trying to survive. And the amount of energy that you're going to get is based on this electron tower and the conditions that put these combinations together. Okay, questions so far? Feel good about this? We'll take a step back and sort of take a look at the variety of different oxidized forms. Okay, here's the oxidized form, here's the reduced form. And basically what you're looking at here is the pair of it. So oxygen is being reduced to water. Okay? We can measure this also to say, well, if I'm going to see this kind of reaction happening, how much enthalpy is actually in the system? How much potential is in the system? Basically, when we see that reaction occurring, we're basically looking at a system that has 0.38 to about 0.32. As the system dries up, you're going to start seeing these other elements being used, or these other compounds basically being used as electron acceptors. They're going to be reduced. And this is the range of EH, or potential, that you're going to be getting off of them. Does that make sense? So what we can do is basically look at these values. We can measure this voltage, and we can basically look at our soils, and we can basically say, if we know what these values are and where they occur, or at what level of energy they occur, we can measure the level of energy that's in the soil and tell you, or tell us, how much oxygen, or more importantly, how much water is in the system. If I have an enthalpy, or a potential, between 0.4 and 0.6 volts, I'm probably in a well-drained soil. As that potential goes down, 0.3 to 0.35, or 0.25 to negative 0.3, we're moving through a flooded system where oxygen is reduced, or ultimately to a prolonged flooding where the oxygen is basically gone. And you can basically look at the potentials to tell you how much water is in the system, or how much water, how much oxygen is in the system. Does that make sense to people? So I can literally use the potential of the system to tell me what type of reactions I potentially will be seeing, and also tell me how much oxygen is in the system, how wet the system, forget about the oxygen, how wet the system is. And it's all being driven by respiration. The redox sequence in waterlogged soils, and this will totally make sense to people, but basically we're starting to see oxygen being depleted due to displacement by water, and low water solubility and consumption by biological activity. Okay? We get water into the system, that oxygen slows down. It can't exchange as fast. So it's got low solubility. It's moving very slowly. Okay? And the oxygen that's in the system is being consumed by respiration. Okay, that's the first step. The second step is, once the soils are depleted of oxygen, anaerobic organisms must use other substances as terminal electron acceptors. That's when we start seeing the shift from this, or I should say from this to these guys. We shift from here to here. As these alternate electron acceptors are being used, the pH starts to rise because most redox reactions start consuming protons. They start consuming those hydrogen ions. Good example of this is the nitrate denitrification, basically taking nitrate and turning it into gas. The NO3 is being used as an electron acceptor, converting it into gas. This is an anaerobic reaction. And in the process, it produces protons, consumes protons. So as a result, the system basically starts getting higher pH'd. You've basically seen something like this. This is CO2 flux. Okay, we were looking at percentages before. This is actually the flux, how much CO2 is actually escaping from a system. So imagine I got a soil here, and I basically have a sort of a trap here, and I'm measuring how much CO2 is escaping from the soil. Okay, basically, again, that measurement of respiration. Well, early parts of the season, when it's cool and wet, not a lot of respiration is going on. But once July and later season starts drying, respiration increases, and all of a sudden we see this big boom in CO2 evolution coming off the soil. Basically just a measurement of the respiration. The ecological importance of this, though, really have huge implications. One, systems aerobic, organic matter is going to be decomposed quicker. Make sense? You get more energy for it, faster reactions. Okay? So, OM decomposition is fastest under oxidizing conditions. Okay? As the system goes reduced, because you're not producing CO2, you're producing other byproducts from respiration, toxic byproducts might in fact be produced. And if that's the case, that will slow down the organisms, which will in turn slow down decomposition rates. Yep. That makes sense. I mean, if I start throwing poisons into the system, I start killing off organisms or stalling them, they're not going to be able to do as much decomposition. So by creating the system, making the systems go anaerobic, I'm doing two things. One is I'm reducing the oxygen content, which makes the amount of energy that I'm going to get from decomposition reduced. And two is the system goes anaerobic. The decomposition products are often toxic, or say decomposition byproducts are often toxic. And that toxicity then reacts with the organisms that are doing the decomposition, slowing them down even more. Does that make sense? Okay. We also have a sequence of reduction or redox of elements. We have certain nutrients, the iron to the iron, oxidized iron, or Fe+3 to Fe+2, sulfate to sulfite. We also have the toxic production of elements. But we also have the soil colors, which we've been talking about for a while, redox colors. Okay? Those colors are predominantly a result of this, but there's also sulfur and manganese and a number of other different colors in there. We also start producing methane. Okay? And methane potentially is a toxic molecule, so back up to this, to other organisms. And we also start seeing a reduction in plant growth. Why? Plants are aerobic. Okay? They need to have, their roots need to have oxygen. They're like us. And if those roots don't have oxygen, and they don't have some sort of mechanism to get the oxygen down, they're going to stop respiring. They're going to drown, basically. Make sense? Okay.
This has been a production of Cornell University, on the web at cornell.edu.